we just had a quick look at cache and saw where we could see what the effect was of going outside of cache lines. But we also could see, hopefully, the size of cache and how that affects the bandwidth that you can see from the and to the cache. These are important things if we're to look at the next aspect of multi-core that is particularly important. And of course, we're talking multi-core without ever having talked so far really about more than one core. But it's all critical stuff on the single core before we get to the multi-core. And why is this? Well, vectorization is the key to be able to get good performance. Meglio? 1, 2, 3? Perfetto. Okay. So, scientists want more compute power. They also want the right results, which always gets in the way of getting faster code, but anyway. So there are 3 main growth areas for flops. One is add more processor sockets. So if you remember what I've said about the machine that we have now and the machine that we had back in 2006, it had half as many nodes, and also there was only one processor, one socket per node, and now we've got 2 nodes. So we've got 4 times as many of these processor sockets, actual physical processors. More cores per socket. That's what we'll be looking at when we have to look at threads and similar, but making the cores themselves more powerful. And the way this has been done is by adding short vector units. So we can't do clock speed increases anymore. That gives us all sorts of problems in power consumption and heat. So we have to use these short vector units. It's really the unspoken powerhouse in some way. We don't really necessarily, when we go along and compile a code, worry about vectorization or anything similar. We just dive straight in and say, but I want to use all the cores on a node. Well, when we talk about on a particular processor, we may have an 8x increase over that period of time in the number of cores, and we want to use them all, but a 4x increase in the floating point power from vectorization, we should really be trying to use that. So if we don't make good use of those vector units, then in double precision, for example, on a Sandy Bridge processor, we'll get 1/4 of the performance, peak performance, at maximum. Single precision, it gets even worse, it's 1/8. And as we go on to new architectures, such as the Xeon Phi, that gets worse and worse and worse still. So, well, what are these vector units that I talk about? They're a set of SIMD units, single instruction, just issue 1 instruction, and then carry it out on multiple data elements. As I said before, people used to have these large vector computers with 256 elements being looked at once. Huge, great vector lengths. And people were able to still get good performance even with this because there was such regularity in their data. They wanted to use it all at the same time. It comes back to the idea we were discussing before about whether you should have arrays of structs and structs of arrays, of course, because you need to have all this data together. But in the olden days, they were much better at gathering data from various areas before working on it, which these processors haven't yet caught up with. Or just as equally, the compilers aren't as good these days. So the units are described in terms of their width in bits normally. So a 64-bit unit can operate on 1 double precision number or on 2 single precision numbers. 64 bits, yeah, 8 bytes, that's double precision. So a 64-bit SIMD unit, and these are the SSE units, and these were the first ones that we were getting on Intel and AMD, actually didn't give us any real bonus in terms of our double precision calculations, but they were useful nonetheless for single precision. Now we've gone to 128-bit units, and now we're at 256-bit units on these SIMD, sorry, in the Sandy Bridge and the AMD Interlagos, if you can use the Interlagos in that way. But particularly for the Sandy Bridge, this is significant. What happens is multiple data items, contiguous in memory, are loaded together into a vector register, and then we issue 1 instruction against that register, maybe a second register, a third register, for example, doing an add or a multiply add. We amortize the cost of doing the instruction decode, which is costly, and then we can just get lots and lots of data out. Now, on some architectures, as we've discussed before, we can get more than one floating point instruction per clock cycle, 4 double precision flops per cycle, plus it's a multiply add. So it works like this, parallel execution. Here on the left is a simple scalar version. It says a C-type loop. Simply taking I, whatever I is, we can just do one item at a time. With vector, we issue just the same number of instructions. That is, it's a multiply add and an equals, but we're able to work on much more data all at the same time. This is a bit of silk notation that Ben will tell you about shortly. But the notation aside, when that actually gets assembled down, turned into assembly language, machine code, that's actually should be the same number of instructions. So we amortize the cost. So how much can we gain through these units? This is the important thing. We said that there's, in theory, a 4x double precision or an 8x single precision improvement over what we used to have many years ago. But they have to be done on regular data. Okay, this is data parallel work. It's not task parallel. If you've got lots of threads doing different things, this isn't about that. That's what the multi-core aspect is about. This is about if you're now one thread going through data, can it work on it in a regular fashion, exactly the same operation, lots of data that's all together. And then it depends very much on the architecture of the machine, what the performance improvement you can expect is. So an Intel Sandy Bridge processor gives us a pretty good performance from what we've seen so far. Now, how can we gain access to these vector units? Well, we could program directly in assembly language, but I wouldn't recommend you do that. And we could use a set of vector intrinsics available with a particular compiler. This is still very low level. And Gilles, maybe, are you going to show that, or have you decided not to? No, you've backed out of that. That's a little too, that was going to be the final optimization stretch in the example this afternoon, because it's a little bit above the assembler, but not too much. So we can use an auto-vectorizing compiler. That's what we're actually going to look at today. Okay, try and get a compiler to help us out to do that work for us. You could also use language which exposes these fundamental types, or something like Silk Plus or whatever, which can also expose that there's vectorization that the compiler can easily peel off. But something such as OpenCL, where there are actual data types that actually define this is a vector of contiguous data, actually also is something where then the compiler says, oh, great, I can deal with that. I can turn that directly into a load into a register, to an addition, etc. Importantly as well, you should always look to vectorized numerical libraries. Let somebody else who's already done the work do the work. So you'll look at matmul later on, but you're looking at it in the context of never write your own matmul unless there's some really special reason, because somebody else has written a better one. There's a lot of better ones out there. Auto-vectorizing compilers. So there's a different set of instruction sets from different processor manufacturers, and we have to find a compiler that can target the right one. So IBM make their compiler for the instruction sets on the Blue Gene Q. And similarly for Fujitsu with the Spark and so on. We're going to look at vectorizing compilers, particularly from GNU and Intel here today, through the use of a very simple example that we have, which is vector addition, and we'll build up to over a period of time to see what things can get in the way and how we can improve things and so on. And the idea is we're taking loops that are written in the serial code that you've written before many times, and saying, what can the vectorizing compiler see there? Oh, actually, I can see that where the dependencies are or whatever. I can see that that's all contiguous data. I'm in a position to turn that into a vectorized code. See, what would be really nice would be if you could issue sort of instructions, the serial ones that we've got. The compiler would just go through, issue serial instructions. The processor at the other side would take these in, and at some point, the hardware would detect, I've got 8 of these double precision numbers together that are waiting on instructions, like all those instructions I mentioned. If it can build up enough, I can issue this in a vector unit and so on. But that would be an enormously wasteful energy-wise thing, and it would be extremely complicated for the processor manufacturers. So instead of that, they pass it out to software and say, at compile time, you work out what is and isn't possible. You give me the instructions and tell me that there's a vector there. So we'll get straight in to looking at vector compilers. So as I said, simple ones we've got, Intel and GNU. Simple vector addition. And we'd like you to carry these compiler examples out on Pilatus. So I'm not actually, Ben will tell you later about AVX and issuing commands to get the correct instructions and so on. Here we're just doing simply what will it do with vectorization out of the box and without vectorization. On Pilatus, remember to load the 2 modules. Because this is C code, we're fine with this. Prigenv Intel and GCC/471. Otherwise, you get the old GCC compiler, which doesn't know certainly about the latest vector commands. It may not know about some of the earlier ones either. It may not do a very good job. And then in this directory with vect, you can pick, the first one we're looking at is simple. In this case, we are doing some coding, so there are some C and Fortran examples. Pick the one that you prefer. And then just go through, look at the timings, try vectorization, try no vectorization. Don't go above 02, because otherwise you might turn vectorization on anyway. And we want you to not have vectorization on for this example to see the difference. So the vectorization you saw could give you some pretty good speed up by getting it, and you get it for free normally, but it only really gives you that sort of speed up if you're in the caches, and particularly the higher the level of cache, the better. So if you're on something such as a finite difference solver or something where you're sweeping through memory mainly most of the time, vectorization may give you something, but it's not going to give you that much because you're mainly, as I said, the very first thing said when we looked at caches, mainly memory bandwidth bound. That's what most applications are about. And so here we're interested in looking at vectorization. So we get good performance improvements in our floating point intensive code in particular. As I mentioned, you can't really see this, but any non-vectorized code in the olden days would work on 80-bit floating point internally. It doesn't anymore. We deliberately try and make sure that isn't happening in the compilers. This is actually a little confusing at times, by the way. Anybody who does look at any assembly language output from a compiler will see these vector instructions being issued, even when vectorization is not turned on. They're not real vector instructions. They're just using the vector registers. But effective use of the cache is also required by changing that vector length and changing the number of iterations. You kept the same number of load stores and adds, etc., but you are now flowing outside of your cache. And you start to see a slowdown even though the vectorization is looking good. So we just tell the compiler to vectorize our code, and by default, of course, it will be switched on in these things. So it does the work. Well, it's not quite as easy as that. Wouldn't it be nice if it was? So there are many times when the compiler can't or won't vectorize your code. There's things where it might say, not quite sure that this is a good idea, or really, I think actually I'm going to have a problem because I can't do that operation until I've loaded the correct data, or you're already using the data for something else. So what we can do is we can get the compiler to issue vectorization reports and see what it's done. Much more importantly than what it has done is what it hasn't done. If it's vectorized something, great, that's what we wanted it to do. If it hasn't vectorized something, we want to know about it and want to know why, and can we fix it? Then we can concentrate on those code paths that are not yet vectorized, as long as they're the ones, of course, that actually take some time in our code. It's like anything to do with parallelism or optimization. You don't waste your time on something that you never call. So we'll have a quick look at some vectorization reports, and then we're going to then Ben is going to tell us a little bit more about the vectorization reports, etc., particularly for the Intel compiler, as an example of a compiler that does give some quite in-depth vectorization reports. So, practical 2. It's very simple. It's like the other one, but now you get it to actually tell you what it's doing and what it isn't. Therefore, it can't vectorize. It can't do anything with that. But we've seen a compiler report. It's pretty simple because it's a very simple code. But the point here is the compiler is your friend. So the vectorizer is going to tell you what it can and can't do, and then in some cases it might even tell you, if you ask it very, very nicely indeed, can you tell me how to get out of this mess that I'm in? So if we combine this with performance analysis tools, then we can see where we should be targeting our code. So if we've got a piece of code which is taking a lot of our time, but which the vectorization report says is not vectorized, that could be a good candidate to go in and spend a little bit of your time vectorizing. If it's not taking any time, don't worry about it. But similar to Amdahl's law, because we're parallelizing after all by doing this vectorization, any bits that you don't vectorize will then slowly become the bottlenecks, but not as dramatically as many of the things that we deal with Amdahl's law. But 8 times performance, the non-vectorized bits then do become a little bit worse. You want to step up now before we move on to other compilers. And so Ben's just going to give us a little bit more detail on the Intel compiler and its vectorization reports, etc. So everything that we've been doing in the practicals and so on is applicable to, in this case, to C or Fortran. So it's a good point to stop before Silk Plus, because that's a C++ only thing, which they've borrowed from Fortran, of course, where we had the things right to begin with. So other compilers give other reports, and Sadaf will show an example of this shortly, probably just after the break. So you can get other reports which may be actually in a nicer to read format. Okay, as Ben said, one of the problems with some of the compiler reports is they can be a bit cryptic and you don't actually necessarily know what's going on, but the compiler reports such as this one from Cray, if you quickly get used to the patterns they put at the top, then seeing this listing delivered back to you with this information is extremely powerful. And the new reveal tool is even better at doing that, and this is one of the things that we actually delayed this course for, so we could show you one of these tools. So use a number of compilers to get a better feel for your code. So far what you've seen is you've seen a couple of compilers, and it's been quite useful, hopefully, to see how they do things similarly but differently. But there are some limits to auto-vectorization that we've just seen. So it can't necessarily do this. So one of the things, for example, we'll see is that non-contiguous data. In the olden days, big vector machines were able to go out and say, well, you're striding through data every 2-4 elements or so on. But I can gather that data into a vector register anyway, and then work on it, and then put it back wherever it needs to go. This doesn't work at the moment with the compilers and the piece of hardware that we have, although there are avenues to go down with the latest processors, the Xeon Phi and so on, to try and get around this, because they're making the vectors so large you have to be able to do these things. But non-contiguous data, we've already seen that it's a problem probably anyway from terms of cache use, but it's also can be a problem for vectorization. Then that inability to distinguish alias data. So one of the examples that Ben just showed was with A and B. You're doing a copy, A and B. Well, what can be wrong with that? Well, the fact is that unless you've got the restrict or some similar, or IVDEP, the compiler doesn't actually know that those two things aren't the same. Now, it's less of a problem normally in Fortran, because the Fortran standard says, well, two different things, they've got to be separate, etc., etc. But if you use Fortran pointers and targets, for example, if you put those things on which not many people do, then actually, similarly, the compiler might say you've got two variables there that I don't know if they're going to point to the same thing. And then we've got the list of vector dependencies. So we're going to look at a simple case here. And when you go into multiple dimensions, of course, this thing can get get far worse for potential dependencies, particularly where you can have potentially overlapping arrays, and it doesn't quite know how things are working. So there are some other inhibitors that we won't be looking at. So we're not going to look at things that might cause problems for conditional statements, reduction operations, but you've just seen on the slides that these things can be taken care of as well and vectorized even now. And some things to do with address boundaries and so on can be an issue on some architectures. The blue gene machines and so on have much more specific problems in terms of the alignment, but for example, with the Intel compiler, as Ben was showing, you can actually tell it things about alignment. So what we're going to look at now is the example of non-contiguous data, just to see what does the compiler tell us in this case. So what we'll do is we'll just grab contiguous, either C or Fortran version, run the example in Intel GNU compiler with the vectorization turned on, and see what the vector report tells us. And then there's a update in there to B. And if you remove it, does it make any difference?
Is it then vectorizing when you take out B statement?
So when you take out the B statement, what does it see instead? Or what is it left with? It's left with your first A array, your first update of A jumping every 2. And then it now sees the next thing.
This starts at 1. I didn't see that.
Yes.
Okay.
So it fills in the gaps. And then it's got all these nice little techniques that we have for loop unrolling and all sorts of things. One of the things is we can split loops, loop fission, or we can fuse loops. And in this case, it says I can fuse that loop and make it just one contiguous loop now, because we've got rid of the B update, which means that things are going to be different in terms of the numbers. So that's not an efficiency thing you can necessarily do, but just to show you how these heuristics will work, it will then be able to fuse the loops. Sometimes it will do fission of loops on very, very large loops if it gets under register pressure. Too many registers will be required to do this, and it might be better to split. But here it's doing fusion. And then it says, I can do that, thank you very much. And off we go into vectorization territory again. Now, you've got to find suitable. This is an artificial example, of course, where we actually do remove certain updates, and you might be able to still get the right answers. In your code, you've got to see if something similar happens. So check when it says that something doesn't seem efficient. Check that it actually isn't efficient, by all means. Force it to do the vectorization. But also see if there's a way of actually getting it so that it's happy doing it. So the thing with contiguous data with SIMD is the instruction sets can only vectorize contiguous blocks of data. So there were these gather scatters, and they're coming back. And the Xeon Phi architecture has been designed so that it will have some of these. I think it's good with the gather, but not very good with the scatter, that sort of idea. Of course, but as I mentioned, the cache-based systems, as we saw this morning, well, if you're missing pieces of data, then you're getting inefficiencies on those cache lines that you have to load in anyway. If you're not using all the data, if it falls out of cache, your memory bandwidth would actually dominate over the vectorization, and you'd be suffering anyway. If you want to get vectorization of code with non-contiguous data, you need to copy it into a contiguous block, and that was related to the question. You can either get a contiguous block in zeros, or you can just get contiguous blocks full stop by compacting things together, whatever's the most convenient and easiest. And that will be done by the compiler for you normally, because it knows what instructions it's got available. So the next thing we'll look at, though, as an example, is overlapping data and aliasing. So, as I mentioned before, you're less likely to do anything like this in Fortran because the actual language semantics tend to disallow much of this. So in this example, we've just got a C code. And this is about aliasing of two pieces of data. Do they overlap? Do they not? Etc. What are the compiler going to tell you in this case? So people managed to get through this exercise? Yeah? Sort of? So what's the difference between these things? Well, the difference is that in one of them we have all of the data available, all the code available that a compiler can see and may be able to make assumptions about data that it's passing in and whether or not it's aliased or not. And say, oh, I could see 2 arrays being passed in. I can make a copy of this particular routine that, because of the way I'm passing it in, that doesn't need to worry about aliasing, and another one that does need to worry about aliasing. The vectorization report should give you some of this information. And then the guide option, as was being described earlier, gives you some feedback and says, this is on the Intel compiler, of course, I really I'm not quite sure about this routine. You could have some data clashes and so on, but if you give me a piece of information about a compiler flag, could be a pragma, etc., a compiler flag maybe in this case, then I can do a better job for you. Then you may be able to get a speed up. And the speed ups here may not be dramatic, but you may be able to see some small changes. You did see some changes? Yeah. Okay. We're going to get a quick example to have a look at a tool we'll see tomorrow that Themis will be talking about tomorrow called Reveal, but unfortunately our speaker's been taken by our director somewhere, so I'll just carry on for now. So you've just seen this example. So compiler directives, Ben talked about. Set of directives to allow the compiler to vectorize, etc. This is a repeat of what Ben's already said, apart from just in this case, this is how you would do it in Fortran compared to how you would do it in C. In C, you get pragmas. In Fortran, we don't have pragmas, so instead, each compiler vendor comes up with what's called a sentinel. And for the Intel compiler, it's $! Sometimes, unfortunately, some of these get repeated. I'm not quite sure whether it's $! or $dir becomes the one for the Cray compiler. And between Intel, Cray, and PGI, 2 of them use the same thing, which can confuse the compiler at times. And so this is just as you will see in OpenMP, same sort of thing, with the $ in the different place. So useful ones are IV, dep, and vector always that I would put in myself. The SIMD one is that one, as Ben was saying, it gets stronger and stronger and stronger. It gets more and more dangerous, okay? Because if you tell it to do something, the stronger it gets, the more it says, you told me to do it, I'm going to do it, okay, whatever. Even with the weakest, with IV, dep, you tell it, I am telling you there is not a dependency in this loop. An example where this comes into play is if you have some sort of for loop or do loop where the final thing you're doing is I plus equals n, or in Fortran syntax, the final thing on a do loop being comma n. Now, you might have to tell it in IV dep just to let it know that n is always positive, or vice versa, n is always negative. Those are the sort of things where you often have to put IV dep in, because otherwise it doesn't know if you can go backwards and forwards, and that would create potentially a dependency for it. So that's compiler directives. Vector dependencies. We'd met before a brief little example. So if a compiler sees a dependency, then it will say, I can't do this. I can't do anything about vectorizing with dependencies. And oftentimes, much of what you're doing with trying to get vectorization working is trying to find the places where it sees a dependency, and you have to say, can I make it so that it doesn't look like a dependency anymore, or just tell it that there isn't a dependency. It's better in some ways to actually try and find a way of reorganizing your code slightly so that there's no dependency visible, or the compiler can see automatically, rather than scattering the IV deps and similar things all over the place. And sometimes that is possible. So there are a large number of these dependencies that can block a compiler. We're just going to look at one simple case in this last little exercise now. And this one is a forward dependency. So you can just grab the CO Fortran example as before from the correct, whichever directory you prefer. And then get a vectorization report and see if splitting a main loop makes any difference.